Hello and welcome to the StorageOS installation demo. Today we're going to install the StorageOS and we're going to show how to use persistent volume claims in a Kubernetes cluster. The first thing we need to do is install etcd. That's a dependency that the StorageOS has, and it cannot be the Kubernetes etcd. We can see that we have 4 nodes, and those 4 nodes are going to install StorageOS. They are worker nodes, and in there we are also going to deploy the etcd. There are different topologies to install etcd. We always recommend to follow the production guidelines for any cluster that has to live for more than 2 days. So production has 2 options: the manual installation of etcd on your machines, virtual machines or bare metal, or the Ansible installation, which is very similar but automated. Today we're going to use the testing because we can install etcd as containers in one command. Again, this is really discouraged for anyone running StorageOS clusters in long living clusters. With this one command, just for testing, we are gonna deploy etcd. Please go and curl this script, check it out. Don't execute anything from the internet, obviously, that is not checked. You will see that it's just a few kubectl commands that will help install the StorageOS operator, the etcd operator. Now we have installed that operator, we have created a custom resource for etcd, and now we can check the pods. We can see that it's starting already the operator and 2 etcd pods, and a third now is going to start as soon as the other one is ready. So as we can see, 3 pods of etcd are starting, and we're going to check the specific service that StorageOS will need to connect to that key value store. So we can see the StorageOS etcd client, and in this case .storageos-etcd will be the service.namespace to access. So StorageOS will reference that URL to connect to this key value store. That is usually StorageOS stores metadata only in that key value store. We're going to follow the official docs of StorageOS in docs.storageos.com just to proceed here with a simple installation. First of all, we're going to create the operator. The operator is a controller that StorageOS implemented, which talks to Kubernetes and registers custom resource definition, which pretty much means that we can tell in a declarative mode to Kubernetes how a StorageOS cluster looks like. And the StorageOS cluster operator will go and create all the resources that compose the StorageOS based on that declarative configuration. The second thing that we need, once we have the cluster operator running, is the secret. The secret is the first StorageOS user and password that will be created automatically for the API. That is also needed to give capacity to Kubernetes to connect through a Linux socket, authenticated Linux socket, to StorageOS. So Kubernetes and StorageOS talk to each other through a CSI socket, and we can generate those passwords based on secrets, on standard Kubernetes secrets using base64 encoding. We can see API username and API password as the ones that are going to be used for the StorageOS API. Therefore, we're going to use that later on for the user interface to access the StorageOS user interface. We're creating this secret in the StorageOS operator namespace, and we will reference it later on. Next step is to deploy the actual StorageOS cluster custom resource. The definition of how a StorageOS cluster looks like from a declarative point of view happens to be that the cluster we're using today is in GKE, but it can be in DigitalOcean, it can be an OpenShift cluster, it can be standard upstream Kubernetes, it can be a Rancher cluster, etc., etc. The only thing we're doing is changing the Kubernetes distro. The cluster operator, the StorageOS cluster operator, will handle the differences that are related to different platforms. We can see in here that there are many options to be configured. These are just simple options. However, there are many more that we can configure. For instance, if you have a cluster without access to the internet, you can specify the specific images from your own registry. So let's go and create this custom resource. First of all, we need to do a few changes. We can change the name. That's going to be the resource name. For instance, we can use the kubecon-storageOS. Also, we can change the address of the key value store. We need to reference that etcd service that we mentioned before, that was StorageOS etcd client.storageos-etcd in the port 2379, which is where the client URL works for etcd. And finally, we can see that the reference of that secret we just created, StorageOS API secret in the StorageOS operator namespace. There are other options that can be changed and can be added in here. You can go and check in the reference section of the documentation for the cluster operator. And we always recommend that for testing, you can put a small request. For production, we always recommend at least 1 CPU and 2 gigs of memory. For small clusters, that's just the defaults are just fine. StorageOS will release memory as soon as it's available, so we don't have to worry too much about it. StorageOS has a low footprint. However, it will depend on the amount of load that your input-output operations are generating on the system. Therefore, if you have a high throughput input-output system or input-output applications, more resources will be needed. We have created that custom resource. It's just a YAML, and actually we can see that from the 4 nodes that are running in our cluster, StorageOS has 4 daemon set pods already ready. So StorageOS by default is created in the kubesystem namespace, and we can see that we already have the 3 main components of the StorageOS. The daemon set, which is actually the main one, then the CSI helper that will help us interact with Kubernetes, and the StorageOS scheduler, which is a Kubernetes scheduler extender or extension that will help influence Kubernetes to know or to put the pods in the nodes where the data is stored, so where the primary volumes are located. In this way, we can achieve lower latency and higher performance. It's not needed. StorageOS can can provision applications or can provision data for applications anywhere. However, it's best to have it close to the data. Now, we're going to use a port forward to connect to the StorageOS service. So all daemon sets, all the StorageOS daemon set pods serve the API port in the 5705. I'm going to use my local host specifically to access to the StorageOS user interface. That can be accessed also with an ingress. However, this tends to be an easy solution for demonstration purposes. So we can see now the StorageOS UI. We can also see the message that indicates that this cluster is not yet licensed. We will do that in the following steps. We can see the 4 nodes that StorageOS is running on. So those daemon sets are generating a StorageOS cluster, and we can see that there are no volumes being used whatsoever. Every one of our nodes have around 20 gigabytes of this capacity, and happens to be that I'm using today the root file system. So we can see that not the 20 gigs are completely available. StorageOS uses thinly provisioned, so only the data that is actually written to the volumes will be used for will be allocated in the root file system. Of course, for production, we always recommend to use different disks, different devices, etc. Finally, we need to license the cluster. We can use the 5 terabyte free license. We just need to register into the StorageOS portal, which actually we'll see as soon as we sign up. Of course, I have an account already, so I'm just going to log in. You can just register, validate your account with your email, and finally just come here and log in. Automatically, your cluster is licensed, it's free, and you have 5 terabytes of provision capacity available. So persistent volume claim capacity. If your cluster is in a closed environment, so it doesn't have access to the internet, just contact us and we can generate a license for you, and you can upload it in this same page as well. Now, as we mentioned before, we already licensed the cluster. our cluster is ready to be used, and we can proceed to our first StorageOS volume. We have in our documentation a few examples on how to create volumes and different use cases. For today, we're just going to create a very, very simple persistent volume claim and pod that uses that claim. First, let me show you how actually a YAML looks like for a persistent volume claim. We can have a standard Kubernetes persistent volume claim that references a storage class that actually is created by StorageOS, and happens to be that in this one we enabled a feature label. We are telling StorageOS to create one replica for that specific volume, meaning 2 copies of the data, the primary volume and its replica. That can also be altered in the storage class. So if we want all our volumes or a few volumes to have a specific label, let's say compression, or let's say replication, 1 replica or 2 replicas. Let's say we have a production storage class and all the volumes in the production storage class need 2 replicas. We can just simply add that in the parameters as a label in the storage class, and all these volumes will inherit that label. Or as we showed before, you can do it at the PVC YAML just by passing labels. Those labels are going to be passed to StorageOS and act upon them. We created the persistent volume claim, and actually we can just start looking at it. That persistent volume claim is already bound, and as we can see, it's in the fast storage class and the StorageOS storage class. We can see that actually the volume is being provisioned. We go back to the user interface and we can see that there is 1 replica available. The volume primary, or where the data is being served from and write to, is in the node 50 JW, and actually the replica is in a different node, and StorageOS will enforce always synchronicity in between the master and the replica. So every time there is a write to that primary volume from a file system, StorageOS will write to the primary volume and to its replica, and when both of them acknowledge, we will give the file system the return code of the successful write. We can see in the node section that the replica is in the node RxVA7 and the primary is in node 50JW. Let's go specifically see this node, and we can see that there is 5 GB of allocated capacity of this specific persistent volume claim. However, StorageOS is not consuming any capacity from that available root file system yet, because actually we haven't used that volume, we haven't mounted anything, therefore there is no data in there. StorageOS used thin provisioning, therefore there is no data until it's written to it. So those 5 GB are allocated in the cluster, yet are not being used in the file system of the host. StorageOS uses the host and any disks that are given to StorageOS in that host to be able to store data from provisioned volumes. We can create the same volume in a different namespace, and we will actually see how StorageOS handles automatically the creation of different namespaces. StorageOS creates that namespace of the PVC that is created, and we can see another volume with its replica. Now we can see that the primary volume and its replica are allocated in different nodes. So we can easily scale horizontally just by adding more nodes to our cluster. Now we can see that we have used 10 GB of the 5 TB available from our license.
Well, thank you very much, Ferran, for doing that demo for us. Are there any questions or anything from the audience?
We do have one question indeed. What sort of workloads can I run on StorageOS? What's it well suited to?
StorageOS is well suited to running workloads that require high performance storage. So things like databases, message queues, things like that work very well. But I mean, essentially, any application that needs read-write once or regular file system storage will work well.
Brilliant. And you guys require etcd, right? Is it possible to run etcd inside my Kubernetes cluster? Is that a recommendation?
So you can run etcd inside your Kubernetes cluster, but it's not something that we recommend for production. The reason for that is that etcd requires a certain number of members to be online in order to have quorum to read and write keys. And if you lose that quorum, it can be painful to recover. And because StorageOS stores its sort of view of the world in etcd, having access to a stable etcd cluster is imperative for the good running of a StorageOS cluster. So we generally don't recommend that you do that. We normally recommend that you run on some other nodes outside the cluster. But if you have well-disciplined ops and developer teams who make sure to set resource limits and requests, and you don't ever have resource contention on certain nodes, then you could run etcd inside the cluster, yes.
That's great, thank you. I think for this session, that's all the questions that we have. So unless any last minute questions pop up, then we'll close out this session.